Okay guys, so welcome to the second half of today's lecture, and in this half we are going to talk about particular sequences xn or pn in R that converge to particular limits. Okay, so it is helpful to know a few sequences by heart, so you don't have to prove that it converges and what it converges to. Before I go on, I'm going to state a theorem which doesn't seem to be in Rudin, but it is helpful, and I think the reason it's not in Rudin is because Rudin think of it as absolutely obvious. So the theorem is something you probably know from Calculus 2. It is usually called the pinching theorem or a squeezing theorem, and the theorem goes as follows: that an, xn, and bn be sequences in R such that an is less or equal than xn, less or equal than bn. And let's suppose that an converges to L and bn converges to the same limit L. Well, in that case, xn also converges to L. Now, this theorem, I think, is almost obvious. It says that if an gets closer and closer to n, and bn gets closer and closer to L, and xn is stuck between them, then it has to get closer and closer to L. But let's give a formal proof. So what do we have to prove? We have to prove that for every epsilon greater than 0, there exists a number n, such that if n is greater than capital N, this implies that xn minus L is less than epsilon. Agree? Now, what does it mean that absolute value of xn minus L is less than epsilon? That means that xn minus L is less than epsilon and greater than minus epsilon. This is exactly the same thing. Okay. Now notice that xn minus L, because xn is less or equal than bn, it is less or equal than bn minus L, and so if bn minus L is less than epsilon, because bn converges to L, that implies that xn minus L is also less than epsilon. On the other hand, xn minus L is greater or equal than what is it? an minus L, right? That's because xn is greater or equal than an, and an minus L for sufficiently large n is greater than minus epsilon. That's because an minus L is less than epsilon. And what that means is that xn minus L is less or equal than bn minus L, which is less than epsilon. Is less or equal than bn minus L, which is less than epsilon, and it is greater or equal than an minus L, which is greater than minus epsilon, and altogether we have xn minus L is less than epsilon, and that's the end of the proof. Okay. So now we're going to use this theorem to investigate particular sequences, and let me start with the first one. The first one is very simple. So the first sequence here is the following sequence. I'm going to take a sequence of 1 over n to the power p, where p is greater than 0, and as you can guess, I'm going to conclude that 1 over n to the power p converges to 0. Now, if p is equal to 1, we have a sequence 1 over n which converges to 0. We already know it from the very first lecture about the limit. It is quite obvious that if p is equal to, say, 1/2, that means that 1 over square root of n, that also converges to 0, as n converges to infinity. I don't think it's much of a deal. So what I claim is that this is true. Okay, and let me prove it very slow. So what do I want to do? I want to make sure that 1 over n to the p, remember this is kind of a background work, it's not something that I want to show to anybody. I want to prove that 1 over n to the power p minus 0 is less than epsilon. Now 1 over n to the power p is a positive number, so it's the same as proving that 1 over n to the power p is less than epsilon. Agree? Which means what? Which means that n to the power p must be greater than 1 over epsilon. Now remember, epsilon is strictly positive, so 1 over epsilon, it may be a huge number, but it's still positive, and if I take the piece root of this number, it will be n is greater than 1 over epsilon to the power of 1 over p. All right, so now take an n to be greater than 1 over epsilon to the power of 1 over p. Notice that once again, at this particular moment, we're using the Archimedean property. Right? Well, in that case, if n is greater than n, this implies that n is greater than 1 over epsilon to the power of 1 over p, which implies that, what? Which implies that n to the power of p is greater than 1 over epsilon, which implies that 1 over n to the p is less than epsilon, because when we take reciprocals, we have to change the signs. And once this is done, you will observe that 1 over n to the p is a positive number, and so 1 over n to the p is equal to 1 over n to the p minus 0, which is less than epsilon, and we're done. Okay, the next sequences will be a little bit trickier, not by much, but by a little bit. And the first sequence that I want to deal with is the sequence for p greater than 0. This time I'm going to take a sequence nth root of p, and I claim that this sequence converges to 1. Okay, so let's see what happens. Pick some p, for instance, I don't know, pick p greater than 1, pick p equals to 2, and take your calculator and compute the square root of 2, cube root of 2, fourth root of 2, etc. And you will notice that these numbers, as roots become higher and higher, these numbers will converge to 1. So the first step that I want to do is I want to prove that if p is greater than 1, then nth root of a p converges to 1. And of course I'm going to prove it in a somewhat non-traditional way, not the way we do it in Calculus 2, because I want to prove it very, very clearly. And the way I'm going to prove it is I'm going to prove that if I choose xn to be nth root of p minus 1, then this particular xn is greater than 0. Why it is greater than 0? Because p was greater than 1, so nth root of p is greater than 1, and xn is greater than 0. And what do I want to do? I want to prove that this xn converges to 0. Okay, so here's a trick, and this will be a trick for the rest of the lecture. You know the binomial theorem. You know that a plus b to the power n is equal to a to the power n plus whatever, n, a to the power n minus 1, b plus etc. plus, here I have n, choose k, a to the power n minus k, b to the power k, plus etc. This binomial theorem is to be known to you. Okay, so now what I'm going to conclude is that if xn is equal to nth root of p minus 1, correct, then 1 plus xn to the power n, well, what is it? It's equal to p, right? Agree? So I'm taking xn equals to nth root of p minus 1. I'm adding 1 to it. I have nth root of p. I'm taking that to nth power, and I get what I want. Now, this is greater or equal than all this stuff in binomial representation, and in particular, it's greater or equal than the first two of those things. So my conclusion is that 1 plus xn to the power n, which is equal to p, is greater or equal than the first two terms here. So a is equal to 1 and b is equal to xn. xn is a positive number, so it's greater or equal than 1 plus n times xn. True? Totally? Well, what does that mean? That means that xn is less or equal than p minus 1 to the power n. Are we good on that? Which is equal to p over n minus 1 over n. Now, from the very first lecture about products and sums of converging series, we know that this stuff converges to 0 and this stuff converges to 0. And so my conclusion is that xn converges to 0 because xn is less or equal than something that converges to 0, and by that squeezing theorem I conclude that xn converges to 0. Are we good? Okay, I hope we are. Let's deal with the next sequence. The next sequence is very similar, except I'm going to use binomial theorem in a little bit more depth. So my next sequence here is the sequence nth root of n, and I claim that this converges to 1. Now, oops. Okay. So I think I'm good now. So while it is true, and I'm going to prove it, and the proof is not going to be very difficult, what I want you to know is that it's by no means obvious. So what you're saying is that if I take 1, and then I take square root of 2, and cube root of 3, and fourth root of 4, etc., then the sequence will get closer and closer and closer to 1. Again, I'm strongly suggesting that you use your calculator and compute a few terms of this sequence to see that for sufficiently large n, this number indeed will be getting closer and closer and closer to 1. Well, okay, so I want you to know that this is kind of the beautiful part of mathematics, in my opinion, because this n inside the square root wants to take the sequence to infinity. When you take the nth root of n, it wants to take this sequence to 1. And so there are like two forces, you know, butting one against another, and one of them wants to take it to infinity, the other one wants to take it to 1, and so that force on the top in the nth root wins, and the particular sequence converges to 1. Alright, so let's prove it now. So this time I'm going to once again choose xn to be nth root of n minus 1. It is clear that nth root of n minus 1 is greater or equal than 0. And once again, I'm going to use binomial theorem to conclude that n is equal to 1 plus x to the n, x sub n to the power n, which is greater or equal than n times n minus 1 over 2 xn squared. Well, where did I get this? Where did I get this stuff? Well, remember that 1 plus xn to the power n is equal to 1 plus n times 1 to the power n minus 1 times xn plus n choose 2 1 times xn squared, and that particularly gives me n times n minus 1 over 2 xn squared. Now this is, so this, you have other stuff here, and this is greater or equal, because if you add something positive to those sums, you will only get greater. Okay, good. This is an obvious inequality, but it's by no means trivial, because you have to choose just the right term in binomial theorems for the things to work out. So what that means is that, what this inequality means is that xn is less or equal than square root of 2 divided by n minus 1. Yes. And greater or equal than 0. And so the conclusion is that this tends to 0, this tends to 0, and so the middle term also tends to 0, so xn does tend to 0. All right. Let's see. Right, so because n is greater than 2 in here, I can get rid of this term, and everything would be great. Okay, so let's take one more sequence, and this sequence is again a non-trivial sequence, and the way Rudin states that this is true is he states that if p is greater than 0 and alpha is a real number, then limit of n to the power alpha divided by 1 plus p to the power n is equal to 0. This looks like a lot of stuff, but the point of this theorem is very, very interesting. So suppose that I take alpha to be huge. For instance, alpha equals to, I don't know, 1,000,000. And on top of this fraction, then I will have n to the power 1,000,000, which is a huge, huge number. And suppose I'm going to take p to be positive, but very, very small, like 0.001. So on the bottom of it, I'm going to have 1 plus 0.001 to the power n, right? So on top I have this huge number, n to the power 1,000,000. On the bottom I have this tiny number, which is a little bit greater than 1, 1.0001, and I'm taking this to the power n, and what I claim is that the limit will be equal to 0. In other words, even though for the first million terms these may seem to be much smaller than the thing on top, and the whole thing will want to converge to infinity, for sufficiently large n, when n becomes a trillion, whatever, a Google, then this number will be so much greater than this number that it will completely outpower this number. Okay, so when you have a limit of a fraction like that, a top of a fraction wants to take you somewhere, a bottom of the fraction wants to take you somewhere else, and then there is a fight between the two, and whoever wins takes it the limit to where it wants to go. In this case, this number 1 plus 0.001 to the power n is so much bigger for large n that it will pass this n to the power 1,000,000 not visible at all. There is a joke that I like about a snail going to a bar, and he bought a few drinks, he had a good time, he had some money in his pocket, so when he came out, a turtle jumped the snail, beat the hell out of him, took all his money. So the snail called the cops, and the cops said, "Mr. Snail, what just happened?" And the snail said, "I don't know. Everything has happened so fast." Get it? So compared to this number over here, this n to the power 1,000,000 is a snail. It's not even visible. Okay, so let's try to prove this theorem. And the proof is, again, using the binomial theorem. But this time what I'm going to do is I'm going to once again take xn, let me use another page. I'm going to take xn to be equal to, what should it be equal to? It will be equal to nth root of n minus 1. No. Okay. So I'm going to assume that n will be greater than 2k. I will explain to you where I'm getting all that. So 1 plus p to the power n, right? By binomial theorem, it is equal to all this stuff, which is the sum of n choose k, p to the power k, okay? And in particular, it is greater or equal than one of those things, n choose k, p to the power k. So just one of them, not the sum of them. And what is that equal to? This is equal to n times n minus 1 times etc. n minus k plus 1 divided by k factorial, right? I'm writing down these binomial coefficients, and I'm assuming now that n is greater or equal than 2k. So I'm multiplying it by p to the power k, and what happens next? Well, remember that n is greater than 2k. It means that each one of those products here on top will be greater or equal than n over 2. So here I will have n to the power k over 2 to the power k, and then I have p to the power k divided by k factorial. Now I'm going to keep k still, and n will continue to grow. In that case, I will have this term tend to 0, right? If n continues to grow, then this term is going to go to 0, because again, this is n to the k, and this is 2 to the n. It comes to the previous sequence. And therefore, this will turn to 0, which proves my theorem. Okay, the last sequence in this particular set of sequences is completely trivial. If x is less than 1, then x to the power n converges to 0. Well, I hope it's obvious. So choose some x to be equal to, I don't know, say 1/2, less than 1, then 1/2 to the power n is equal to 1 over 2 to the power n, which definitely tends to 0. Agree? Good. So the whole thing tends to 0, and another way around to do it is I'm going to take our previous sequence, and the previous sequence is over here with the where is it? This sequence, right? And if I take alpha in this sequence to be equal to 0, then the whole thing is trivial. Okay, agree? Agree. Okay. So these are the few sequences that we will need to know in the future, and that ends the part of a chapter that deals with sequences. On Thursday, I'm going to deal with series, and again, much of it will be very similar to what you have studied in Calculus 2, but there will be proofs, and some of the proofs will be non-trivial, and it will be using the theorem about convergence of the sequences that we learned today. So I will upload the next lectures for Thursday.